Most Python developers imagine a function as a box holding lines of code. You define it, you call it, and the box runs. But if we look closely at how cpython works, that box is completely empty. To see what is really happening under the hood, we are going to trace a single standard method call, d.bark. We will track exactly how this specific call moves through the system, step by step, all the way down to the bare metal. In cpython, a function object contains no executable logic. It is strictly a metadata routing node, a container holding contextual variables, and a map to the real destination. Separating function routing from execution logic allows systems programmers to diagnose performance bottlenecks by tracking the movement of memory pointers rather than the arrangement of syntax. Before we add the parentheses to execute our call, we need to map the geography of the cpython memory heap at rest. This diagram shows the pre-execution state of our program. Suspended here are three isolated memory blocks. First, at hex address 0x2000, we have the py function object. This represents our bark method. Next, sitting at address 0x3000 is our instance object d. This holds the specific state data of our particular dog. And finally, at address 0x5000, we have the bytecode object. This is where the actual compiled bytecode instructions reside. Right now, these three structures are physically separated. They are just distinct pockets of data sharing the same physical heap. The process of execution is the dynamic, real-time wiring together of these isolated blocks into a single continuous circuit. A Python program, before it runs, is simply a scattered collection of data waiting for structural alignment. The instant Python evaluates the text d.bark, it triggers a descriptor lookup. A descriptor lookup intercepts attribute access, dynamically retrieving our method from the class dictionary instead of the instance dictionary. To bridge the gap between the instance and the function, Python allocates a temporary memory structure called a bound method object. This bound method establishes a direct pointer named imfunc, which builds a route to our function definition at 0x2000. Simultaneously, it creates a second pointer named imself, routing directly to our instance state d at 0x3000. By locking these two distinct references together into a single callable entity, Python ensures that when the function finally runs, it knows exactly which specific instance it is operating on. The bound method exists entirely to hold this specific state linkage in memory before we process the execution trigger, the open and close parentheses. Let's follow that imfunc pointer entirely into the function object at 0x2000. Looking inside the C struct of the py function object, we find a list of metadata slots. It holds pointers to dictionaries for global variables, default arguments, and keyword defaults. Notice what is missing. There are no raw executable instructions in any of these structural slots. Instead, there is a single exit path, the func code pointer. cpython relies on this specific pointer to bridge the gap between the context assembled in the function object and the raw instructions required to act on it. Following the func code pointer across the heap leads us directly to the bytecode object at address 0x5000. The function object acts as a network router. It exists to provide context and point the interpreter to the final destination. We have now arrived at the bytecode object memory block. This structure is the static, immutable core of all cpython execution. Inside, we find two specific data arrays. The first array is co-var names. This acts as a rigid, indexed registry for every local variable the logic will need. Right here at index 0, the array strictly maps a spot for our self parameter. The second array is co-code. This is the final resting place for the raw, compiled bytecode bytes. These bytecode instructions cannot be modified during runtime because they contain no dynamic state. They only know what operations to perform, not what data to perform them on. By isolating the bytecode object like this, cpython achieves massive memory efficiency. Thousands of different method calls across a program can all point to and reuse this exact same static bytecode instance. Everything we have mapped so far has been set up. It is only when Python processes the actual parentheses of our method call that a completely new runtime environment is allocated. This environment is the execution frame. It is a temporary, highly structured memory block. Watch our instance pointer at 0x3000. It physically detaches from the bound method and securely injects into index 0 of an array called locals plus inside the frame. Locals plus is a contiguous block of memory optimized specifically to store local variables and intermediate stack data. Because the code object expects the self parameter to be at index 0, this specific injection is how self receives its actual runtime data. With the frame populated, the interpreter shifts focus to the bytecode instruction waiting inside the bytecode object. Load fast 0 is an explicit command telling cpython to read whatever pointer currently resides in slot 0 of the active execution frame. The operation successfully retrieves our instance pointer from the frame array. The execution frame is the critical collision point where the immutable bytecode instructions finally intersect with our volatile runtime state. We have our target data. Now we trace the final trajectory of the 0x3000 instance pointer as it leaves the execution frame. The pointer hands over from cpython's software layer directly into the hardware layer, locking into a CPU register. At this exact moment, Python's abstraction ends and bare metal execution initiates. Every method call, regardless of syntax complexity, reduces to this singular action. At the hardware level, execution consists of the precise chronological delivery of memory pointers into a register. Looking at the fully wired circuit, we see the complete end-to-end memory pipeline mapped out. This strict separation of concerns makes this architecture incredibly powerful. Code objects provide reusable logic. Function objects provide routing context. Bound methods handle state linkage. Frames isolate runtime variables. The underlying mechanism orchestrating all these pointer movements is the interpreter loop. cval.c is the C source file inside cpython that reads bytecode instructions one by one and executes the corresponding C code to physically manipulate this memory. In modern Python versions, this path is further optimized by the vector call protocol. Vector call is a fast path execution engine designed to pass arguments via a C array, minimizing the overhead of building these intermediate objects. Understanding this system as a choreographed topology of memory pointers provides the structural visibility required to optimize Python at the architectural level.